Right, so here we're going to take an s orbital, our px, our py, and our pz, and we're going to combine our 4 atomic orbitals into 4, 1, 2, 3, 4 sp3 hybrids. Right? They've all got all of these hybrid orbitals have this kind of bowling pin looking shape to them, where they got a big lobe and then a little lobe. Right? They're bigger and broader than the p orbitals on the one end, and then smaller on the other. Right? And then all together, they're going to occupy a space that points to the corners of a tetrahedron. So in our carbon, we're going to take our 4 atomics, and we're going to combine them into our 4 equivalent hybrids, right? Rather than being at 90 degrees to each other, right? These guys are now going to be pointing at all of the corners of our tetrahedron. So now our geometry is happy, right? Our energy is happy. We have solved some problems with our Lewis structures and our electron configurations by developing this idea of hybridization. Right? So now we've got these guys pointing at the 4 points. Right? One of them is going to do an overlap with this hydrogen's s. So we've got an sp3 orbital here overlapping with a hydrogen's s, and we're going to form a direct overlap, and that is a sigma bond. For molecules with expanded octets, we can do the same thing. Here is phosphorus pentachloride, right? Nothing in our initial VSEPR shapes matches up with any of those atomic orbitals when we're talking about something that's this complex. Like, how do we get expanded octets? Like, if we got 2 in S and 6 in P for a total of 8, what's going on? Why can we have these expanded octets with some of these things that are in our in row 4 and higher, right? So it's because they're going to be able to use some of these d orbitals to do that. So in our phosphorus pentachloride, right, we're going to take an S, 3 Ps, and 1 D. So we're going to basically make it all into lone electrons, and then we're going to hybridize it. So we're taking an S, 3 Ps, and a D. So we've got 5 atomic orbitals, and we're going to make 5 hybrid orbitals. Right? And when we do that, we're going to end up with a shape that is going to match that trigonal bipyramidal shape that you would expect for something that has an electron domain geometry with 5 things around it. Now we've got our 5 sp3d, right? So 1 s, 3 p's, and 1 d. Right? This is going to make an sp3d. Each of these sp3d orbitals is able to overlap with a p orbital from chlorine, and this overlap here, that's our sigma bond. Right? So kind of as a review for some of these things, if the number of electron domains on your central atom is 2, you're going to be sp hybridized, right? So in order for you to get your VSEPR shapes, you have to do this hybridization, right? On that central atom. So here, our geometry for a linear one is going to be sp2. All of our trigonal planars are going to be sp2. Our tetrahedrals are all going to be sp3. Our trigonal bipyramidals are all going to be sp3d, right? So the number of things over here is going to be equal to the number of electron domains, right? To get an electron domain, I'm going to take that many orbitals. Number of orbitals. I'm going to need that many hybrid orbitals that are going to come from our atomic orbitals. Now, you can have this hooked up to another atom. So, like, let's say we make a hydrogen over here, or this guy maybe is just going to be a lone pair, right? This guy could be a lone pair. So, like on water, right, H2O, we've got an oxygen atom, we've got a lone pair, we've got a hydrogen, we've got another hydrogen, right? And then we got another lone pair that would be kind of going out into the hinterlands, right? Right, so I've got an electron domain geometry of 4. The oxygen atom is going to be sp3 hybridized. Even though my molecular shape is bent, my electron domain geometry is tetrahedral. If you've got a tetrahedral electron domain geometry, it's going to tell you what that hybridization is. Right? So if you've got 2 charged clouds, it's linear, it's SP. 3 charged clouds, trigonal planar, SP2. 4 is tetrahedral, SP3. Right? So here is that same chart we saw earlier with our VSEPR shapes, right? Number of bonds, number of lone pairs, number of charged clouds, but I have gone through and I've added what the hybridization is for this as well. So all of our trigonal planar stuff, for example, right? All of these, because they're in that trigonal planar electron domain geometry, all going to be SP2 hybridized. All of these guys in here that are tetrahedral electron domain geometry are all going to be SP3 hybridized, no matter how many atoms we've got on there or how many lone pairs. Right? Same thing with when we get to our trigonal bipyramidal. Those are all going to be SP3Ds, and all of our octahedral guys are going to be SP3D2s. All of the bonds that we have considered so far have been single bonds. We are also going to call these sigma bonds, right? So how do I remember this? Right? Single, sigma, and that is the Greek letter sigma, from which we get the letter S. Right? It is a bond resulting from the overlap of 2 orbitals and is going to be symmetric about the axis joining the 2 atoms, or end-to-end overlap. Right? So if you looked down with your eyeball along this axis, it's going to be the same. Right? Overlapping orbitals are going to have a circular shape to them. Right? Double and triple bonds consist of both a sigma. You're always going to have that. And you're always going to have a sigma. Right? So when you do your Lewis structure, right, like let's say carbon and an oxygen, CO2, right, you're going to draw that initial bond, right? That's your sigma bond. And then when you have to go through and do your double bond, right, that is going to be your pi bond. Right? So this second one is going to be your pi. And that's just kind of an oversimplification on paper. We'll take a look at what that actually looks like a little bit more. Right? So our pi bond results from the overlap of orbitals, both perpendicular to the axis joining the 2 atoms. Right? Sometimes they're called a pi bond. Part of why they're called a pi bond is because this was first observed in things that have p orbitals. Right? So p for pi. Right? So, and it is a perpendicular, right? Perpendicular pi bond, p orbitals. Right? So they're going to kind of look like p orbitals, where I've got this orbital over here, right? This p orbital for this dude, and a p orbital for this carbon over here, and I've got this region of overlap in 2 places where those things can overlap, right? And so that's what it looks like when you first put them together. So the sp2 hybridization leaves one of our p orbitals unhybridized, right? So we've gone through, we've got this trigonal planar structure in here, right, between our hydrogen and then, oops, that's going back a ways, and that's to the carbon, and then up to this other hydrogen, and then this guy's connected to the other carbon over here. So this trigonal planar shape, right, that's accounted for by taking these 3 orbitals, an s and 2 p's, to give us the 3 sp2 hybrids, but then we got this one dude that's left over. Well, this one dude that's left over can do the same thing as this carbon, and we can overlap and take this guy's carbon and bring it into here, and they can share. All right, so for ethylene, which is a C2H4, we've got this double bond in here, right? We've got this sigma bond backbone, right? There's a sigma between the carbon and the hydrogen, and between the carbon and the carbon, and between the carbon and the hydrogen, and the carbon and the hydrogen, right? Those are all sigma bonds. Then we have this leftover p orbital, right? And those p orbitals are going to combine to form like these little hot dog buns on either side. All right? So you can either have your end-to-end touch, or you can have a hot dog bond. Right? So our pi, there are 2 lobes of our pi bonds kind of merge together to form one big combined orbital across those 2 atoms in our double bond. Right? So the number of electron domains in both carbon is 3, which means its hybridization has got to be sp2. Right? So we make some sp2 hybrids out of our s's and p's. Right? That's going to form our backbone. We've got 1 double bond. So we've got our double bond consisting of both this sigma bond here and this end-to-end overlap here. That's our pi bond, right? A triple bond is going to look similar, right? Here's the same thing, just kind of tilted a little bit, right? So you can see where we've got our trigonal planar going on here, right? A sigma bond overlap between our two carbons, right? And then this big pi bond over here. That's on both sides. Right? If we have acetylene, C2H2, it's got a triple bond in here. Right? It is, both carbons are going to have an electron domain geometry of 2. Right? I got 1, 2 things on it, one single bond and one triple bond. So that means that our hybridization is going to be sp. So we'll take our carbon, we'll excite it, we'll then combine 2 orbitals to give us our sp, which makes us have that linear domain geometry. Now I've got 2 leftover unhybridized p's. Right, so the first thing we will do is we will combine our sp orbitals from each carbon into a sigma bond, or a single bond. And our triple bond is going to be 1 sigma bond, which we just saw over there. Right? And then we'll have 2 of these big hot dog type shapes. Right? So we're going to have these y p orbitals making 1, and then we're going to have these, it looks like x p orbitals over here, these x's, right, making another hot dog shape on this side. Right? So we've got 2 sets of these big, long, overlapping hot dog shaped orbitals. Right? They're 2 pi bonds and 1 sigma bond. Right? So if you're counting up bonds, I've got 1, 2, 3 sigma bonds in my molecule, and 1, 2 pi bonds. Right? So how many pi bonds and how many sigma bonds are in each molecule, and describe the hybridization. So looking at this guy first, right, our chloromethane, right? We've got carbon, carbon, hydrogen, hydrogen, right? Each of those is a sigma bond, so we've got 4 sigma bonds, right? Looking at this one over here, we've got 1, 2, 3, 4, 5 sigma bonds, and 1, because it's a double bond, pi bond. On this one, we've got well, I'll draw these out. This one's tricky because we've got 3 hydrogens, right? So that's actually a hydrogen over here, and a hydrogen over here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sigma bonds. And for pi bonds, we got 1, and then here we've got 2. So I've got a total of 3 pi bonds. Right. Looking at the hybridization on this carbon is going to be sp3. It's got 1, 2, 3, 4 things around it. Its electron domain geometry is going to be tetrahedral. It's going to be sp3. Here around this carbon, right? This carbon here, that's going to be 1, 2, 3 electron clouds around it. I'm going to need 3 orbitals to do that. It will be sp2 hybridized. Right? Looking over at the next carbon over, same deal. It's also got 3 things around it, sp2 hybridized. Looking at this carbon, it's got 3 hydrogens and another carbon over there, sp3 hybridized. This carbon in here has this hydrogen, one going to this carbon, and then this triple bond over here, it'll be sp2 because it's got 3 things around it. Looking at this carbon, it's got 1, 2, 3 things around it. It's also going to be sp2. This carbon here, which is only hooked up to 1 carbon on the left and 1 CH on the right, is going to be sp hybridized. Right? I need to get 2 orbitals to give me my 2 bonding centers. And then this carbon over here is also going to be sp. Right? So our problem-solving strategy when doing this is, 1, draw the Lewis structures. Right? That's going to be first. Hook your atoms up together, make sure they've got the right skeleton and the right backbone. Then you're going to determine the arrangement of the electron pairs in the 3-dimensional shape using our Vesper model. Right? Then you're going to specify the hybrid orbitals needed to accommodate the electron pairs. Let's look at an example. For each of the following molecules or ions, predict the hybridization of each atom and describe the molecular structure. So we're going to do carbon monoxide, boron tetrafluoride, anion, and xenon difluoride. We'll start off with carbon monoxide. The carbon monoxide molecule's got 10 valence electrons, and its Lewis structure is going to look like this. It's going to be a carbon triply bonded to an oxygen. If you wanted to do the formal charge on this, this guy here is going to be an oxygen. That'll be a +1, and this carbon over here will be a -1. It's not a super happy molecule, but it'll stick around. Each of these atoms has 2 effective pairs, which means they're both going to be sp hybridized. So this carbon's got this lone pair, and then we've got something going to the triple bond. The oxygen is going to have the lone pair, and then something going to the triple bond. So they're both going to be sp hybrids. Our triple bond is going to be a sigma bond. That's going to be our end-to-end overlap from our hybrid sp orbitals. And it's going to have 2 pi bonds produced from the p orbitals, both our py and our px, that are going to then form those long hot dog shapes. Right, there's a hot dog, and then there's a hot dog. And then looking at it this way, coming kind of towards us out of the plane of the paper, we're going to have a hot dog between this part here, right? And then we'll have one in the background. That'll be this guy, okay? So we've got 2 pi bonds and 1 sigma bond. Right? In boron tetrafluoride, -1, we've got 32 valence electrons. The Lewis structure is going to look like this. And I've got 1, 2, 3, 4 things around it, which means they're all equal. We're going to end up with a tetrahedral electron domain geometry and a tetrahedral molecular geometry, which means it's got to be sp3 hybridized. I got 4 things around it. It's going to need 4 orbitals. When we combine them, the fluorine's got 4 electron pairs that can also be sp3 hybridized, or we can just go into the p orbital, but the BF4 ion's molecular structure is going to be tetrahedral. Right. In our xenon difluoride, the molecule has 22 valence electrons. The Lewis structure shows 5 electron pairs around the xenon atom. Right, so we've got 1, 2, 2 things, and then a lone pair. 1, 2, 3. So I've got 3 lone pairs, 2 bonds. I've got 5 things around my xenon, which means it's going to be my trigonal bipyramidal structure. Right? For us to have a trigonal bipyramidal structure, it's going to need to have what kind of hybridization? Right? I'm going to need 5 things. So I'm going to have a DSP3 or an SP3D. Either way is fine. I like to do it the other way rather than DSP3. This one's a little weird. Each of the fluorine atoms has 4 electron pairs that can be assumed to be sp3 hybridized. In our xenon difluoride, the molecule is going to have a linear arrangement of atoms, right? So our molecular geometry is linear. So our molecular geometry tree is linear. But our electron domain geometry is going to be trigonal bipyramidal.